As I've mentioned earlier, 380 Electronic Circuits Lab is about design, simulation, breadboarding of relatively simple analog circuits. And the first circuit that you would be designing is a integrator using an opamp. And so prior to designing the integrator and designing, simulating, breadboarding, what we would like you to do is understand the opamp, which is 741, a little better. And you do that by measuring a few of the parameters of the op-amp. Okay, so the objectives are then two. The first part of the experiment is to measure a few of the parameters of op-amp. Of course, is a complicated entity with many parameters, but what we want is for you to measure a few of the op-amp parameters of 741 op-amp. I'll talk about it, and then the other part is designing an op-amp integrator, simulating it and breadboarding it and testing the op-amp integrator, okay? And the specs of the op-amp integrator are given over here, and we'll discuss that shortly. All right, so this was a part of a slide that I had shown in the last lecture, which is a simplified view of how design proceeds. And as I said, design starts with a set of specifications, and then you go through the design process, typically using simplified device model. And after you obtain the circuit schematic, what you do is you simulate the circuit using more accurate models that allows you to check whether your circuit would, when you build it, whether it would satisfy the specs or not. And once you are, you look at the results, and if you're happy with the results that you get, then it's fine. Then you go to the prototyping and the fabrication stage. If you're not happy, you of course iterate back to the design process. You make changes so that your design gives you the required characteristics, right? So this is a simplified view of what you do in design. Now, even this part, if you look at this part here, you're given a specs and you're going through the design and obtaining a circuit schematic. The remaining part is more of tuning the circuit such that it gives you the, if your specs are not properly satisfied, you tune it so that it satisfies it here. If we go and look at this particular part here, this part also you can, if you wish, you can break it up in phases. For example, I've shown you, so let me talk about this particular part here, okay? The design process. The design process itself, I can break it into two parts here. If you look at it, the first part, again, we have specs, and we're going through a design process here. And this part of the, you're just starting the design. This is a very creative part of the design. Creative part where you're trying out different circuit schematics, and typically it helps if you work initially with an ideal device model. The reason being is that, as I said, it's a creative phase where you're doing rapid iterations in your mind or on paper, trying out different schematics. And you want to use a very simplified device model because you don't want to be burdened with a very complicated model. If you generate an alternative, some kind of a design, and you want to evaluate it, and your model is so complex, you won't be able to evaluate, right? So this part of the design phase is a creative phase. It requires rapid iteration. And it works best when you use very, very simplified device models. And in our case, then it turns out to be ideal devices, like ideal diode, ideal op-amp, and similarly ideal elements here, right? So you work with those ideal elements and come up with a design here, a circuit schematic. Now, obviously, because you work with an ideal element, when you actually implement it with the practical, it's not going to work. There'll be some problems here. So now what you do is, the design that you've obtained with an ideal element, now you do an analysis with slightly more realistic element here. For example, you may carry out a design using an ideal diode. Now, what you do is you evaluate your design using maybe a 0.7 volt model, right? So you use a slightly more realistic model and you evaluate it. And based on that, you refine your design. You refine your design and then obtain the final schematic here. So note that circuit simulation is not coming into picture here. This is the initial part of the design that I'm talking about here. That initial part itself, you may work with different levels of complexity of the models here. You may work with ideal elements here and then gradually add more of non-idealities here and then make the schematic work with those non-idealities. And then finally, after you're done with it, then you evaluate using a very accurate model, using circuit simulation. Okay, so as an example, we'll soon see that, I can use an ideal op-amp that you see here, ideal op-amp, which all of you are familiar. I'll just talk about it. So we can use an ideal op-amp, and using an ideal op-amp, we can very easily show that if I take an R and a C, it works as an integrator. So we come up with a schematic of an integrator that you see here, right? Using an ideal op-amp model. But then what we do is we go ahead and look and know that the op-amp is not ideal. It has several non-idealities. And we'll soon see what those non-idealities are. Now, when we evaluate this schematic using those non-ideal op-amp, we find that this particular schematic will not work because of those issues here. And we'll see that what we need to do is we need to add another element RF here in parallel. And now when you add this, now this one takes into account some of the non-idealities of the op-amp and is a more practical circuit that is here. Of course, even now you're using an op-amp model which is not the most accurate. So what you would do is you would take this particular schematic and then simulate it, right? But note that the design process itself is being broken into two parts. One is with an ideal element, right? And as I said, this is a creative part. If you go and talk to psychologists, they'll tell you the number of elements of information that you can hold in your brain is roughly seven or less. So you don't want to be burdened with too much information at this particular stage. It's a creative phase, and you're connecting a diode, transistor, element, op-amp, all of those things, and trying out different things. You don't want to be burdened by a very accurate model at this stage here. So you work with ideal elements, and then come up with a solution. You know that is not going to work. It will have problems. And then you refine that particular solution here with more accurate device model. And then further refinement takes place when you go and simulate. Okay, with a more accurate model here. All right, so as I said, this particular experiment is based on a op-amp, and it's a very simple integrator that you have to design. And let me come back then to a discussion of the op-amp here. All of you know that very often we work with an ideal op-amp element, and ideal op-amps are elements, it's like an ideal voltage amplifier with infinite gain, infinite bandwidth, infinite input resistance, zero output resistance. And since op-amp is a differential element, the inputs are differential in nature, there is infinite CMRR. There are virtually no limits on input, no limits on output. You can apply any inputs, you can get 40 volts, 50 volts output. There are no limits anywhere, right? No limits on gain, no limits on bandwidth. It's an ideal element, right? And so, but we know that no op-amp is ideal, right? Which means that any op-amp that I take, this is not going to be infinite. This is going to be maybe large, but a finite value. Similar, for example, for a 741 op-amp, this may be, say, 100,000 gain, 10 to the power 5. Bandwidth is not infinite. It may be a megahertz only. Some better op-amps may even have 100 megahertz, 1 gigahertz bandwidth. For your 741 op-amp, it would be close to a megahertz. Input resistance is again not infinite, maybe a mega ohm. Output resistances are again not zero. These are all finite values. This is all again non-zero here. CMRR, again, all of them have finite values or non-zero values, right? So, and this is something we know in general that, models range from simplicity to simple to more complex, and accuracy is how it goes here. Anyway, so let's come back to this ideal op-amp. And one of the properties of an ideal op-amp that you know is that when you put a negative feedback in an ideal op-amp, this point becomes a virtual ground. Virtual ground meaning the potential at this particular terminal is same as the potential here. And many of the circuits, this terminal is made ground, so we call this as a virtual ground, right? And this is a mistake that we commonly see students making it, especially in the lab. They think virtual ground is like ground. And therefore, I can actually connect a ground here at this particular point, okay? Realize that this virtual ground is a very special ground. And some people like to say that, this particular property is simultaneously short as well as open. It's short. Why? Because the voltage here is the same as the voltage here. So you consider it as a short. Why do you consider it as open? Because no current really flows here between these two terminals here. So it's like a short and it's like an open also, right? So it's not if you go and make this particular point ground, your circuit is not going to work. So keep in mind, it is the virtual word is important. It's a virtual ground. Okay, it's not a real ground here. Anyway, so this point is we know that the voltage here is 0, and based on that property, a whole wide variety of circuits are made. This, of course, is a very simple amplifier, and based on that, we can design an integrator. Instead of a amplifier with a resistor here and a resistor here, all that you do is replace the resistor by a capacitor here, and you can very easily evaluate this particular circuit. You know this is virtual ground, so the current here is V in by R. This current will not flow into the op-amp, will flow here. The arrow shows the current will flow through the capacitor. Current through the capacitor is C dV naught by dt, minus sign because this is 0 here and this is V naught. And then, of course, rearranging, you show that V naught is minus 1 over RC integral V in dt. So there you have a integrator. So whatever input you apply, this is going to integrate that particular input, and the output would be given by this particular relationship. All right, so we have a integrator which we have built using an ideal op-amp. Now we know that real op-amps are not ideal. They'll have a variety of non-idealities, and amongst them finite gain, input resistance, and all of that here. Okay. Now some of these things are you're familiar. So what I'm going to point out, some of the non-idealities that are going to bother you in this particular design here. All right, these are something called input offset voltage. Besides the fact that the gain is finite and input resistance is also not infinite and output resistance is limited, those are not going to bother you. The fact that let's say the input resistance is 1 mega ohm, right? So the input resistance, let's say between these 2 points is 1 mega ohm. It's not going to bother you. The reason being is that even though the resistance between these 2 points may be only 1 mega ohm, the voltage at this particular node will be typically very small because of the feedback. The voltage at this particular node will be small here. So any current which flows here because of input resistance will not be very large here. It's not going to bother you that much. Similarly, the output resistance being, let's say 10 ohms or 20 ohms is also not going to bother you. Okay. The things that will bother you here are some of them that I've listed. Input offset voltage, I'll explain in a minute. Input bias current, bandwidth may bother you. Something called slew rate may also bother you. Okay, so I'm going to describe these parameters here, and these are the parameters that we will ask you to measure in the lab as well. The bias currents, the offset voltage, the bandwidth, the slew rate. Okay, so these are things that may be new to you. Okay, all right. What is this input offset voltage here? Now, if you take an op-amp, say ideal op-amp, and you make this inverting input ground and non-inverting ground, obviously what would you expect at the output? 0, right? No input is there. The difference between these two is 0, so you would expect output to be 0. What I would suggest is when you go to the lab to do this experiment, take your 741 op-amp. Here in these, by default, assume that the power supplies are connected to the op-amp. Typically plus 12 and minus 12 for the 741 op-amp here. So even if I don't show, please assume that there is a power supply connected here. So if you take your op-amp in the lab, put a ground here and put a ground here, what would you see in the lab? You're not going to see 0. You're not going to see 0. What you would see is very likely either if your power supply is 12, you're going to see some voltage likely to be plus 11, close to 12, or minus 11. That's what you will see here. All right. So a huge difference between an ideal op-amp and a practical op-amp. You go and apply both inputs ground, and you're going to see plus 11, 11.2, 11.4, or whatever, or minus. It could be that. Some of you may see a plus, and some of you may see a minus. That also is there. Okay. Now the issue is, where is it coming from? Where is this extra voltage coming from? And if you go back and look into the reasons for it, the reasons are that within your op-amp, as all of you know from your prior background, there is a differential pair and there are other amplifiers. And in differential pair, one of the important properties of a differential pair is that there should be matching between transistors, matching between resistors. And what happens is, when you go and look inside, let's say a differential pair like this here, the left side here that you see a differential part here and the right side here, they're often not matched. The transistor here may have slightly different properties as compared to a transistor here. The two resistors that you see here, they may be nominally 1K or 10K, but no two resistors are exactly same. So because of these mismatches, what happens is the output voltage is not zero. So what happens is, because of these mismatches, a voltage is generated here which is further amplified by the next stages, and because the op-amp has very high gain, eventually what happens is this mismatches cause the output voltage to go to plus 12 or minus 12. And because these mismatches that you see here are random in nature, your op-amp, let's say when you are working with it, the mismatch may be such that, let's say, the beta of Q1 is larger than beta of Q2. In some other person who's working with the op-amp, in his op-amp, it may happen that the beta of Q2 is larger than beta of Q1. And therefore, the mismatches, by their inherent nature, they vary from op-amp to op-amp. And that's why the results of the mismatch will be different. In some of you, as I said, may measure plus 11 volt, and some of you may measure minus 11 volt. It's quite possible here. Okay, so the source of that voltage is what we call as mismatch. The result of mismatches inside it. Now, what we do is, now we know that there are mismatches. We know that even if I don't apply any input voltage, there is an output voltage. How do I model it? Well, all the effects of the mismatches that are there inside your op-amp, what we do is, we take its effect and lump it in a voltage called the input offset voltage. So, what I'm saying is, you have a practical op-amp. You can think of a practical op-amp with all the mismatches as if it is an ideal op-amp in series with the input offset voltage. All the effects of the mismatch are all lumped into this parameter called input offset voltage. Because remember, any mismatches, any beta variation, any resistance variation, finally, how does it manifest itself in an op-amp? As some voltage, right? Any change or anything, electrically it manifests as a voltage here. So its effect can be modeled also in terms of a voltage here. And that's how we model it. We model it in terms of an input offset voltage here. So all op-amps then will have a quantity called input offset voltage, which is a measure of all the mismatches and all of that inside the op-amp. Right? So this is a parameter. So your op-amp, what is available to you are these two terminals here. So think of your op-amp as if it's an ideal op-amp with no mismatches, but in series with a voltage inside it. There's no real voltage, of course. It's just a model. The voltage is just mimicking the effects of all the mismatches that are there. Okay? So input offset voltage then is an important property of an op-amp here. So now the issue is, we want to measure this input offset voltage. Okay? We'll see how to measure that. The other non-ideality that you need to bother about in a design of an integrator is bias current. In an ideal op-amp, we say the current going into the negative terminal, the current going into the positive terminals are all zero. But that's not true, as all of you know, that inside a op-amp, I have a differential pair. If I have a bipolar transistor, you know that is biased. There would be this positive terminal maybe going into the base of a transistor here, and you know that the transistors are biased in forward active mode, and therefore a current is required here. A current will flow in, and a current would flow in here as well. So real op-amps will have a current, DC current going in, and another DC current may be going into the op-amp as well. So these are what we call as, because these come about because of the biasing, so we call these as the bias current here. Because of this comes from the input part of the circuit, and so it's the input bias current here. So your op-amp will have certain amount of current flowing in this terminal and certain amount of current flowing in this terminal. Ideally, the two currents should be the same. But in practice, it is not, because the two transistors are different from each other. Their betas may differ a little from each other. So this current, IB minus, may be larger than IB plus, or IB plus may be larger than IB minus. So we also talk about input offset current. Input offset current is what? The difference of these two values here. So you have bias current, and then you can also talk about what is the difference between these two currents as well. That will be called input offset current here. So that's another non-ideality to keep in mind here, that I have these currents in my op-amp. I've shown you the data sheet of a 741 op-amp. You can see here the input offset voltage. If you go and see, they quote a value of 0.8 millivolt, typical value. But they also say that it can be as large as 3 millivolt here, which means that it's going to vary. It's going to vary from op-amp to op-amp here. Similarly, the input bias current that you see here, the input bias current, the value that is listed is 30 nanoamperes. But again, that's a typical value. They also say it can be as large as 80 nanoamperes also. So these quantities again vary. Okay. And similarly, there are other parameters that you can look at here. So now the issue is, should you bother about, if you look at the values here, I have maybe 1 millivolt of offset voltage, and I have 30 nanoamperes of bias current. Should I bother about these small values here, 1 millivolt? If the input voltage that I apply is 5 volt, and the currents in my circuit that are flowing are in milliamperes, should I worry about 30 nanoamperes of current here? Should I worry about 1 millivolt here? Well, that of course depends on the circuit. In some circuits, it would be important. In some, it will not be. In our case, it does bother us. That's why I'm talking about it. For example, I said this is an integrator, RC. If I try to build an integrator using an ideal element, ideal op-amp, this is what I would build. Now, note, I have not applied any input here, but we know that at the positive terminal, what do I have? An input offset voltage. Think of it as if there is a voltage applied to your op-amp, even if you don't apply anything here. So what will this input offset voltage do? Now, what is this? This is an ideal op-amp now, in series with a offset voltage here, which is mimicking all the non-idealities. What will this offset voltage do? Well, we can analyze now, because this is an ideal op-amp. So voltage here is VOS, let's say 1 millivolt. The voltage here will be 1 millivolt, right? Now this 1 millivolt, what will it cause? A current to flow here. 1 millivolt divided by R. So let's say R is 1 kilo ohm. So 1 millivolt divided by 1 kilo ohm. So you have how much? 1 microamperes flowing. Where will this current flow? For a moment, let's not bother about the bias current. This 1 microamperes will flow through the capacitor. What will happen to the capacitor? It will start charging. And it will start charging. And this is what you will see here. Even if you're not applying any input, the capacitor will start charging, and it keeps on charging. Eventually what happens? The value saturates. Because you know that the op-amp output will not go beyond the supply voltage here. Right? So it goes and saturates here at this point. So a very small voltage here, what it will do is it will saturate your op-amp. So you are somewhere here. And then when you apply any signal here, the op-amp doesn't respond to it because it's saturated. It's already into 12 volts here. Right? So a very small voltage here is bothering you because it causes a current to flow here, and this current flows through this particular capacitor, and therefore it keeps on charging the capacitor even if no input is there, and as I said, eventually it will saturate. So 1 millivolt of offset voltage bothers here. So which means what? We designed the circuit RC using an ideal op-amp model. Now that I have a more realistic op-amp model, I know that it's not working. It's not going to work. How do I overcome this? Well, you know that why it is saturating is because this small current is flowing through C, through this capacitor here and charging it. This current will always be there. Now, if I don't want it to charge my capacitor, I have to provide an alternative path for this particular current here. So what I do is, I will put another resistor here in parallel to provide a path for that current to flow. Okay. Now look at how that was offset voltage. Look at how the bias current bothers you. As I said, the current going into this negative terminal, there is a small current which is going in. Maybe it's 30 nanoamperes. Okay. Now, so there is a current going in. Now, where will this current come from? Note that right now we are not bothering about offset voltage. We are looking at each effect one at a time. So this point is ground. If this point is ground, because I have negative feed, this point is also ground. Okay. If this point is ground, the current through the resistor is 0. So this current that you see here, where will it come from? It will flow again through the capacitor here. So this bias current that you see here, it actually takes a path, starts from here and goes through the capacitor and comes here. So again, what will happen is it will charge up your capacitor here. So this small bias current also will flow through the capacitor and will start charging it. And the op-amp again will saturate, eventually will saturate. So again, you have to provide a path for this small current here. IB minus that you see here, you have to provide a path for it. And both of these things that you see here, whether it's the input offset voltage here or the bias current here, what you find is you have to provide a path for those currents here, and we do that by attaching another resistor RF here. Okay, a resistor here which provides a path for it. It doesn't go through the capacitor now, and therefore the op-amp does not saturate. But now you note that R and a C is what gave you an integrator. Now you have to connect an RF in parallel to C here, and your integrator is no longer ideal. So if I analyze this particular circuit again, so as I said, the basic idea is to provide a path here, but my integrator now becomes non-ideal. Because remember, it was R and C itself which gave a integrator here. So I can analyze it again by saying V in by R. Now in this analysis, now note that I'm not doing a very accurate analysis. I'm not taking into account offset voltage. I'm not taking into account bias currents and all that. I'm just showing that if you connect an RF in parallel, then V in by R is the current that flows here, minus C dV naught by dt minus V naught by RF here. That's the set of equations. You solve it, and what you find is that the output voltage for a for a step, let's say if you apply an input which is a step here, so what you find is that it goes exponential. It charges, this is what I'm trying to, it charges exponentially, rather than if this term had not been there, then you know that the V naught, dV naught by dt is for a constant input voltage is constant and the charging is linear. Now when you have this particular term here, even if you apply a constant input voltage, you know that the charging becomes exponential. And discharging also becomes exponential. So this is what I'm showing you here. If you apply, let's say, a square wave, your integrator may show a charging which goes like this here and a discharge which goes like this here. Now, what we want is an ideal integrator. We want the charging. If it's a good integrator, it should go as linear. Linearly charge and linearly discharge. And we see that there is non-ideality in the integrator. And this non-ideality is coming. Why? Because we have to put an RF here. Now, you may be wondering that I'm talking about offset voltage and bias currents and all that. Why didn't I take this into account? As I said, I'm doing approximate analysis. And not only that, this RF that I've put here, I've put it of such a magnitude and all that, that I manage the effects of offset voltage and bias current. Manage in the sense that this RF minimizes the effect. It allows a path for the bias current to flow. It applies a path for the DC current due to offset voltage to flow here, and sort of keeps these effects under control. Keeps the voltage resulting from bias current and offset voltage to be small, and so that this equation is reasonably valid. So the whole idea of putting an RF is to minimize the impact of offset voltage and bias currents here. So you have to design it like that. Okay, you have to choose RF to minimize those effects here. Okay, so what we have to do is, as I said, in the first part of the experiment, you have to measure the opamp parameters. Now you must be wondering, why measure the parameters when the manufacturer has already given it to you? I just showed you the data sheet. The manufacturer has given you 0.8 millivolts here, 30 nanoamperes here. So why measure it? Why should you measure it? The values are already given. So why are we asking you to measure? Okay, so what you're saying is, for your op-amp, the value is going to be different. Okay, all right. So I grant you that for your op-amp, the value, you want to know what the value is, whether it is minus 1 millivolt or 1.5 millivolt or whatever. But remember, why do you want to know the value? You want to design a circuit. Now, are you going to design only one circuit? I mean, who designs one circuit? You know, if you have a product in mind, you have to, you know, you're fabricating and selling, if not millions, lakhs or thousands of such circuits. So when you design, you have to design it in such a way that it doesn't work for only 2 nanoamperes of bias current. It has to work for the whole range. So when you design it, you will have to design keeping in mind what? The maximum offset voltage that I can have. Right? So you will design it for the worst case scenario. So why do you want to know the specific current that flows in your op-amp or the specific offset voltage that is there in your op-amp? Why do you have to know it? You have to design for the whole range so that the circuit works. Right? And specifically, you have to design for the worst case scenario. So I will design it by taking the maximum value that the manufacturer is saying for 3 millivolt. Similarly, if the manufacturer is saying 80 nanoamperes, I'll design it for that. If it works for 80 nanoamperes, it will work for 0 nanoamperes also. So I'll design it under worst case scenario. So why measure again? Well, the main reason why I want you to measure is the following. Measurement of these parameters would inculcate greater appreciation for conditions under which these parameters become important. What we want is for you to understand, when will these parameters become important? These are new parameters to you. When will they become important? Now note that when you want to measure a offset voltage, what do you have to do? You have to design a circuit such that nothing else matters except the offset voltage. You're designing a condition in which the effect of offset voltage is really magnified so that you can easily measure it. Similarly, if you want to measure the bias current, you're designing a circuit or you're designing a condition in which the effects of bias current are really magnified, because then you can measure it easily. So you're creating conditions under which these effects are magnified. And in some sense, when you create those conditions, then you will have an idea of when will these parameters become important, under what conditions will they become important, so that next time when you are doing, designing some other circuit, you will have an idea looking at the circuit. Should I bother about offset voltage? Should I bother about bias current? If the conditions prevailing in that circuit are similar to the conditions that you will design in this particular one. So the main idea is that when you design circuit, when you measure it, you will get a better appreciation of when these parameters become important. Otherwise, we have the values with us. We can work with it. Okay. So, for example, if I want to measure offset voltage, so what I do is, again, remember that this is a part of the opamp. It's just being showed this is a part of the opamp. So I'm not applying anything, right? So what I do is, so all this is a part of the opamp, and I make a circuit with an R1 and an R2. Okay, no inputs applied. I make an R1 and an R2. So now think of the opamp as ideal. And what does it have? In addition, there is a source here, VIO, and there's a current IB minus. Now you analyze it like any ideal opamp circuit, because this element is ideal. And you can very easily show that V0 equal to 1 plus R2 by R1 into Vi0 plus IB minus into R2. Vi0, if you look at, you're using superposition because all these voltages and currents are small and it's a linear circuit. So Vi0, this is nothing but a non-inverting amplifier. So you get 1 plus R2 by R1 and IB minus flows through R2 and you get this, right? So you can see this is telling you when will the effects of offset voltage be important. Whenever you are building a large gain amplifier, let's say you didn't bother about offset voltage at all, and you are building an inverting amplifier, non-inverting amplifier. What is the gain of non-inverting amplifier? 1 plus R2 by R1, right? So whenever you try to build a large gain amplifier, well, there would be a contribution from Vi0 also to the output, independent of whatever signal that you apply here. Anyway, so if I'm interested in offset voltage itself, what should I do? Well, I want to, increase this particular part here, contribution here, and minimize this particular part here. So obviously, I should use R2, which is small, right? So that this becomes relatively small here, while I want to, increase the gain here, R2 by R1, so that I can easily measure the output voltage here. So all you have to do is adjust your R1 and R2 accordingly, such that this effect becomes more prominent and you are able to measure it here. Okay, but this is the governing equation which allows you to estimate the value of Vi0 here. So you build this particular circuit, you measure the output voltage here, and from V0, you'll infer what is the value of Vi0. Okay. All right. Bias currents, how do you measure? Well, if you look at, suppose you're interested in IB minus here. So what you do is you build this simple circuit here. And now, again, no voltages are applied. You can easily show that V0 is equal to Vi0 plus IB minus this current here that you see here, IB minus or IB1 into R. So now in this case, you would like to put a very large value of R because you want to magnify this effect here. So this term becomes large here, and you want to minimize the effect here. So if you build a large enough resistor here, this term becomes more important, and V0 will be will give you this IB1 value here. And if you know the value of Vi0 already, so you can do some correction as well. Okay. So similarly, these are very simple circuits. It will take you very little time. All you need to do is put an R here, measure the voltage here. Similarly, the other bias currents, you put an R here and you measure the voltage here, and you'll get the value of the other bias current as well. So very, very simple circuits, trivial in some sense, through which you will get the values of input offset voltage, bias currents, and IB1 and IB2 here. Okay. Something which requires a little bit more effort is the fact that your op amp has a finite bandwidth, which is shown over here. That if you, as I said, your op amp has a finite gain, open loop gain is maybe, let's say, 100 dBs. Now, if you take your op-amp under open loop condition and measure its frequency response, what you would find is, note, this would be a typical characteristics, 100 dB gain starts falling, and then eventually this is a log plot in dB, the gain falls to 0 dB at around 10 to the power 6. So note that you probably thought that your op-amp is wide bandwidth. What is the bandwidth of your op-amp? The gain of your 741 op-amp may start falling at 10 hertz. 10 hertz is where it would start falling, right? And then gain keeps on falling. At 1 megahertz, the gain of your op-amp is 1, close to 1, right? Now, remember, the ideal op-amp, one of the chief characteristics of ideal op-amp was very high gain. And that very high gain was what was allowing you to use the virtual ground property. Now, if you're over here, gain is 100. Can you use virtual ground property? The answer is no. Virtual ground property will not hold here at this point, and certainly not here. The gain of the op-amp is 1. So don't think of op-amp as a very high gain amplifier always. Yes, it's a very high gain amplifier at lower frequencies, but the gain of the op-amp is false and becomes, this frequency is what we call as the unity gain frequency here, FT, where the gain falls to 1 here. So one of the measures of how fast an op-amp is this particular frequency, FT, unity gain frequency, and therefore we would like to measure it. FT, how large FT is. And so if you want to know how your op-amp behaves, a very simple picture of an op-amp is that the op-amp's gain is a function of frequency, which is given by this very simple first order transfer function here. AL0 is the gain at lower frequencies, and it falls as 1 by JF by F3 dB. That's it. And F3 dB is written as FT by AL0. Okay. So that's how your op-amp actually looks. It's a high gain amplifier, but only at lower frequencies. And as you go to higher frequencies, the gain falls. Okay. Now, for an integrator, this is going to bother us, because if I'm trying to integrate a higher frequency voltage, then my entire analysis was based on virtual ground. And now I don't have a virtual ground. Okay, so I have to be on guard. If somebody tells integrate a 100 kilohertz square wave, integrate a 100 kilohertz square wave. So if you're 100 kilohertz is somewhere over here, your gain of the op-amp is very small. You can't assume a virtual ground property. Okay, so you have to be aware of the fact that your op-amp has a finite bandwidth here, and which is very simply shown over here. So what we want you to do is measure the unity gain frequency of your op-amp. Go ahead and measure it and see that the op-amp has a finite bandwidth here. Okay, and how do we do that? Well, we do that by building an amplifier. You can't work with op-amps in an open loop gain. Open loop mode, the op-amp is very sensitive. You apply a little bit voltage here, and immediately it goes to plus 12 and minus 12. So working in open loop is very difficult. So what we do is we make an amplifier. We make an amplifier that you see here, a normal inverting amplifier. But we don't say that the gain of this amplifier is R2 by R1. That R2 by R1 is based on the fact that this point is virtual ground, which is no longer true, because we know that if you go to sufficiently high frequency, the op-amp's gain is very low, and this point is not virtual ground. So what we do is we reanalyze this particular circuit with a slightly better model. And the better model is, we again take, even though these things are, input resistance also becomes smaller and all that, but slightly better model where we model the op-amp as a voltage control voltage source, as you can see here. Voltage control voltage source, and except that the gain that you see here is a function of frequency here, this gain. So we model the op-amp now no longer as an ideal element, but we model it as a finite gain, and the fact that the gain varies with frequency. So now I can take this particular circuit and analyze it. This particular circuit with this kind of a gain function here. And if I analyze it, I can show that the gain here of this amplifier, V0 by Vin, can be written as minus R2 by R1, which you are familiar. But along with that, this term comes 1 plus JF by F beta. What does F beta means? F beta means nothing but the 3 dB frequency of this whole amplifier. Okay, and you can show from this analysis that the 3 dB frequency of the whole amplifier is related to unity gain frequency of the op-amp through this relationship. So what we do is then we build this amplifier in the lab and we measure its 3 dB frequency, which is very simple. We measure its 3 dB frequency. You know, you build an amplifier with a gain of 100, you change frequencies, measure the gain, and you plot it out, and you get 3 dB frequency here, F beta. And then we use this relationship to get the unity gain frequency of the op-amp. So that's our way of measuring the unity gain frequency. Okay. All right. So this is the circuit that we build, and from there we estimate here. So you'll get a plot like this. The 3 dB somewhere you'll identify, and you'll use that formula to obtain that. Okay. One more non-ideality of the op-amp, which is the slew rate. Okay. Now, I don't think we'll be left with time to discuss the integrator. We'll do that in the next lecture here. So I'll just finish with the op-amp characteristics. So slew rate, the basic idea of a slew rate you can understand by first looking at this RC circuit here. Now, if you look at this RC circuit here, right? This RC circuit, as all of you know, if I analyze in the frequency domain, I'll get this transfer function, 1 by 1 plus j omega RC. RC is the time constant here. If I analyze it in the time domain, I apply a pulse here. Well, the output will charge exponentially, discharge exponentially with a time constant, which is 2.2 hours. With a, what is this time constant? Time constant, of course, would be simply RC, okay? Not 2.2 RC. Time constant will be RC here, okay? All right, it would take, to reach 90% value and all that would be 2.2 RC, okay? So rise time and fall time will be this particular value. Of course, it depends on how you define rise time and fall time, okay? 3 taus or 4 taus or whatever, okay? Don't worry too much about this parameter here. So anyway, rise time and fall time would be some number here, 2, 3 times RC here. Now, as I said, if you recall, I've been saying that your op-amp can be modeled as a first order transfer function here, okay? If I connect it in this particular mode, unity gain feedback mode, op-amp can be talked about as 1 by 1 plus j f by ft here. Now, if the op-amp can be modeled like this, then if I apply a signal here, what I would expect is my output would rise exponentially, fall exponentially. So we are modeling it as a first order transfer function. So it should rise exponentially and fall exponentially here. However, I'm giving an example here. So say your ft is 1 megahertz. You can do calculation and show that the rise time should be about 0.35 microsecond here. It should rise up in 0.35 microsecond, fall down in 0.35 microsecond here, if this picture is correct. But then, if you actually apply a large voltage here, especially if you apply a large voltage here, you find that the op-amp output is not changing exponentially, and neither is it falling exponentially here. In fact, you would find that is rising linearly, and in this case it saturates, but otherwise it would rise linearly here, reach its peak value, and then fall again linearly. It's no longer changing exponentially, which is basically telling you is that this simple model is not correct. The simple model works fine if your input voltages are small. If input voltages are small in magnitude, it's okay. It rises exponentially, falls exponentially. But if the voltages become large, it rises linearly and falls linearly. And this linear rise and linear fall is what is called as the slew rate here. Now the reasons are, I don't know whether did we see that in 210 slew rate? No, we didn't do that. Okay. All right. In maybe later courses, you'll see the reasons are that actually there are capacitances inside your op-amp, and there is a finite amount of current which is available, and the charging and the discharging get limited by the current. Okay. So basically what slew rate is that there's a maximum rate at which your output voltage can change. If, dV0 by dt, there's an upper limit on that value. And that value is what we call as the slew rate. If your dV0 by dt is less than the slew rate, then it's fine. The op-amp is, the rise time and the fall time is determined by the input. But if it exceeds this particular value here, the op-amp takes over and says, no, that's the maximum rate at which you can change the output. And this is the largest rate at which the output can fall. Okay, so that's like an upper limit on the slopes. Okay, you can't exceed that particular slope because of the internal limitations on the currents inside the op-amp here. So this is also an important part, important limitation of the op-amp here. The maximum slopes are limited to the slew rate here. And I'll skip that. So slew rate is, you can see here, the manufacturer quotes roughly a value of around 1 volt per microsecond. So the maximum rate at which your output voltage can change is 1 volt in 1 microsecond. It can't go beyond that. Okay. Now, so that's another thing that you should keep in mind here. Now, will it bother you? Now think about, suppose I had, I taken a circuit, and instead of a square wave, suppose I put a sinusoid here. If I put a sinusoid here, say 10 volt or 8 volt or whatever sinusoid here, what do you expect at the output? A sinusoid, right? Because it's a buffer. So you expect a sinusoid. But then, as you increase the frequency of the sinusoid, what happens to the slope? dV0 by dt? You know, sinusoid has slope. Where does the sinusoid have maximum slope? At the origin, right? It has minimum slope at pi by 2, so it has this thing. Now, if it starts exceeding the slew rate, what will happen? Well, the op-amp says you can't exceed a certain rate of change of output voltage here. So what you would start getting is a distorted sinusoid, because the op-amp is not able to follow that high rate of change of output here. So you start getting a distorted sinusoid here. I think I'll show you. Since we don't have time for an integrator, I'll show you the slew rate. Just see that when I apply a sinusoid here, and the frequencies are 100 hertz, this is input and this is output. You can see both input output look like very good sinusoids. We changed it to 1 kilohertz. Even now, both sinusoids are fine. We change it to 20 kilohertz. Can you begin to see a distortion here? It's not following, and you can see it more clearly here. The input is a sinusoid. The output looks like a triangular, because it's not able to follow the slopes here. So the signals then become distorted. The sinusoid becomes distorted. Similarly, if you feed in a square wave, it will get distorted. It will not be a very nice triangular wave. Yeah. Okay. So slew rate is something that you need to worry about. The other one is the offset voltage. As I said, when you measure it, this was I've plotted results that were obtained by 10 students here. So you can see one student obtained, this has not been plotted very well here, -1 here. Somebody, 2 students got a value somewhere in this range here. So what you're going to measure is different values. And so there is no, you can't say, is this correct? Right? As long as it lies, as long as you don't measure 100 millivolt. If you measure 100 millivolt, there's something wrong. But if you are measuring 2 volt, somebody is 2 millivolts, somebody is measuring -2 millivolts, somebody is measuring 5 also. Maybe if somebody is very lucky, very close to 0, that may also happen. That you have a device and you keep on adding and you're saying, sir, I'm not finding any voltage at the output. It's quite possible. Either you're making an error, or it's quite possible that your op-amp doesn't have any offset voltage. That's also possible. That is very, very small. You know, it may be a few microvolts. That's also a possibility here. Okay. All right. As I said, I don't have time to discuss the op-amp. So in the next particular lab, we'll discuss the design of the op-amp. Okay. So let's stop here.